what we want to do is really to answer these questions over here, right? If you go back to the slides, we asked about whether or not this is the correct specification for ML out, and whether or not this will be the correct specification for ML in. We want to know, right? And of course, both of them should only be concerned about the changing the value for variable n. That's the only variable we have in concern. What about changing d? Well, be careful. D is a constant. Of course, we cannot change it, right? It's a very a basic question to just make sure you actually didn't get confused. All right. So now what I would want to do is I want to informally justify whether or not the current specification for ML in and ML out is actually correct, right? Correct in the sense that it is not possible for us to really let these two events occur in a particular order such that the invariant will be falsified. Let me write it down. Okay, so the question really is, let me write down the question here, and then we're gonna see how we can build the abstract state machine. We'll see. Okay, so now R ML in and ML out specify correctly such that there is not a trace. I'll talk about what a trace is in a moment, leading to invariance violation. Right? That's something we'd like to see. Okay, let's now ML in. Are they specified correctly such that there is not a trace that will lead to invariant violation? There is not. All right, so that will be something we'd like to see. And I claim that there is such a trace which will lead to invariant violation. Okay, and in order to really show such trace, I need to give some concrete value, just some example configuration. Let's start with this. Okay, I got this state template over here already. Let me try to use it. Right, I'm gonna build the so-called abstract state machine, and we have some initial states over here. And for the initial states, remember we're gonna put an arrow over here just to say this will be where the system is first initialized. And let's say the constant value is going to be 2. So what does that mean? That means in this island and bridge compound, maximum 2 cars can be there at any given time. If we are able to actually interleave the occurrences of ML out and ML in such a way that we got maybe more than 2 cars in the island and bridge compound, in that case, that means our design for the events is simply flawed because it allows such invariant violation to occur. Right? Hopefully that makes sense to you. Right? What about initially? Well, of course, this initial value over here will be up to our design for the very special initialization event, which we'll talk about later. But for now, it definitely makes sense to say maybe whenever the island is actually open for every day, we assume that there should be no car, maybe to begin with. Well, maybe at the very beginning, when the island was first opened, for like a grand opening, in that case, there should be like a no car in the compound to start with. Right? The counter should really start from 0. That's my point. So why don't I simply just put 0 over here? All right. And what we should really make sure is every state should really satisfy the invariance. All right. That's something we want to make sure. Okay. So now, does this satisfy the invariance? Well, 0 is a member of the natural number for sure, and also n less than or equal to d. 0 less than or equal to 2, right? So that's something. Remember the invariance I that we spoke about, right? We're going to say I will be, by definition, n is a member of the natural number, and conjunction n is less than or equal to, in this case, it will be 2. So let me just put 2 specifically. So this will be the invariant condition that every state, starting from the beginning, it should be established, and also between any state transition, this invariant I should be preserved, right? That's the thing we want to keep in mind. All right, and in this particular states, what are the events that's being enabled? Well, both events will be enabled because in this case, as we said before, the guard for these two events will be as if they are simply declared as true. So both are enabled, right? So that means from this state, I can either say ML out or I can say ML in, right? That's what I can say. Well, let me just give you one example over here. What if I actually got, let's say I got one state transition over here, like an arrow over here, because I know that ML in is actually enabled. So I can definitely let ML in to occur. So once ML in occur, let me now put the resulting states. What's going to happen over here, right? You want to think about exactly how to make a state transition. As far as ML in is concerned, it's going to somehow make sure N after the state transition over here is going to become N minus 1. So N minus 1 is going to be 0 minus 1. So you get, well, let me put it again. The N value after the state transition is going to become its value before the state transition minus 1. That's exactly what this part is really mean, right? So you can make think about this colon equal to over here is about something like a becomes, right? It may not be so advised to think about it's more like a variable assignment. I would not really recommend. That's also not recommended by the textbook, because now what we are really doing here is not programming. What we are doing here is about specification. So you want to think about what this really means over here is the N value after the state transition is going to become the N value over here on the right hand side, which is before the state transition, minus 1, right? So that's going to be 0 minus 1, which will be minus 1. All right. This is a valid transition because this event is simply enabled at any time, at any states. However, is the resulting states satisfying the invariant I? Well, apparently not, because you can see minus 1 is not a member of the natural number. So we have broken the invariance. We have broken the first one, right? Hopefully you can see what I'm trying to do over here. Okay, so now you can see over here. So this one, let me use the pink just to say it's not green. Let's see this. In the very beginning states, the I was satisfied. Okay, so that's why I can simply put the I over here is actually satisfied. Check. However, in this case, it will be not the case I. It is not specified. So this will be a states violating invariance I. Okay? What's really the trace? The trace is we simply take ML in the beginning. So the trace we can write as a sequence like this. It will be a sequence of ML in, just like that. Just a sequence of a single events. That's how we can write a trace. All right. Hopefully you're okay with the first counter example. And I'm gonna do one more. Okay. So this will be example number 1, which will show that we didn't really have a good design for, at least for ML in, because somehow ML in should be constrained, should be disabled, maybe in the very beginning of the states over here, because in that case we can prevent from N to be decremented from 0. All right. Hopefully you're following this, and let's now do one more. Before I do the second counter example, you can feel free to pause the video and think about what kind of trace would you have to show that ML out is actually inappropriate, given that ML out is always enabled, right? Kind of in a very similar way as this. Maybe you need a longer trace. That's my hints. Okay, you can pause the video and think about it. All right, assuming that you thought about it, let's check your answer against mine. So what I would do is I'm running out of space over here, so I will put the counter example over here, right? I'm going to put it here. So example number 2, which is intended to show that ML out, this event, is actually inappropriate, meaning that we can actually have a trace that will lead to violation of the invariance. Let's see how. Okay, so again, let me just copy the template over here. Actually, I got it on the clipboard. Okay, let me make it smaller over here. I think it's still visible, right? I think that should be good enough. All right, let me copy this small version. Right, we're gonna have initialized to be. Initialized to be let's say the value of n would just be 0 as before. All right, and we know that this initial state is going actually satisfies the invariance. So I put a green over here. So far so good. And if I try to do ML out, all right, if I try to do that, so that'll be the state transition I'm making. And let me use the blue for the state transition, right? If I try to make a state transition over here of ML out, right? ML out. Okay, so according to it simply say that the n value over here in the so-called post states. I'll talk about pre and post state again, maybe in the next part of the lecture. The n over here in the after the transition is going to become its value before the transition plus 1, right? So that one is going to be 0 plus 1, which will be 1. Does this resulting state satisfy the invariance? It does, right? You can see 1 over here is definitely a natural number. And also 1 less than or equal to 2 is also true, right? So that one also satisfies the invariance. That's not a problem. So far, we haven't got any violation for the invariant, but we're going to keep going. You can kind of see you can actually see where I'm going actually. Okay, we got one more over here, right? Right, we might just need to make a little bit more space over here. I'm pretty sure you know what I'm doing over here. Okay, all right, and let's now do another one over here. And that one there is going to take just another ML out. Okay, this is also going to be ML out. Okay, that will be the second transition, and it's going to do something similar. It's going to say m is becomes m plus 1. So that we go from 1 to 2, right? Think about what's happening over here. We let the car simply the first car into the mainland, into the compound, and then the second car will first car go to the compound, and then the second car go to the compound, and we allow a third car go to the compound as well, because the MLR is always enabled, right? That's actually how we created a violation for the invariance. Right, so this one here also will satisfy the invariance. I'm pretty sure you can check it. You can see 2 over here. The n is less than or equal to 2. Also, it's a natural number, right? All right, the final one I'm going to put will be over here. Let's see if I can just move this a little bit upwards over here. Okay, right, good. Let me now put the final states over here. Okay, let me put it here. And the final one is going to be just one more ML out. Okay, ML out over here. Does this satisfy the invariance? Well, first of all, what should be the value for n? It's going to be 2 plus 1, which will be 3, right? So now if you look at that, 3 will be the value for n. Over here, 3 less than or equal to 2 is going to be false, right? So that means over here, we actually got some violation for the invariance, right? So let me simply just put that it's not a case that invariant I is actually satisfied. So that will be a trace. So what exactly is a trace? Let me just write down the trace, and then we are done for this example here. And I will just recap what you should really remember what you learned from this part of the lecture. So the trace that leads to a violation for the invariant will be, we simply got ML out 3 times. ML out, ML out, and also ML out. Right? It's a sequence, right? Because it is the beginning of the sequence, that's the end of the sequence. So that'll be the counter example that we have. So this was the first counter example for ML in, and this is the second counter example for ML out. So informally, we justify that the design for ML out and ML in are inappropriate because at the moment they are simply completely enabled at any given state, which will lead to a violation for the invariance. This is one example for ML in, and this is one example for ML out. However, the way we actually show this violation is by giving some concrete value for n and also d over here, which is not exactly how Rodin, like a theorem proving approach, is gonna proceed with the reasoning. But that's something we'll definitely see what kind of a proof obligation we have to discharge at the abstract level in terms of the predicate. That's something we'll see later. All right, let me recap very quickly. It's quite a bit of a discussion over here, but don't lose the big picture. This is our state space to start with for our initial model. That's the abstraction. And based on the abstraction, we know that we want to monitor the change of the variable n over here in the compound for the island and bridge. And there are two possible ways to really change this value over here. One would be when there's a car moving from mainland into the compound, or when there's a car moving from the island, moving from the compound into the mainland over here. One will be +1, the other one will be -1. Make sure you understand that. And then we talk about the design for ML out and ML in. And typically there should be a when part over here. The when is a keyword for the event B modeling notation. Where under the when part over here, there will be some Boolean, maybe a list of Boolean conditions specifying the guarding condition for the events, meaning that when the guarding condition of an event actually evaluated to true in the current states, is going to be enabled. But for both ML out and ML in, since they don't really have the when part, that means it will be as if the guard is simply true, meaning that these two events are always enabled. And I would say typically, if you see any event that will do some updates but it's always enabled, that might be a warning sign. That may be a no-no, right? But of course, you got to justify that. And rather than giving some formal proof, what we do is we try to simply give you some counter example over here directly, right? What we really want is to make sure every state is universally true. It should be universally the case that every state that the state transition can really result in should really satisfy the invariance over here. But we can show you that by having a single, by having a trace where there's only a single occurrence of MLN, we can lead to some invariant violation. And by having 3 occurrences of ML out from the initial state, we can also have some invariant violation. That's how we justify like these two events are actually inappropriate. Right? Make sure you understand this approach over here of finding some counterexample. That's actually quite important. Right, let me switch back to see if I miss anything. Actually, that's fine. So, correct specification, no. Correct specification, no. So we're gonna revisit the design over here later to also fix them. All right, that's something we'll do later. All right, so then the next part, I want to talk about briefly how we can formalize the actions of the events as before after predicates.